Once again, hi folks. Welcome to our weekly YFTT, Yugabyte Friday Tech Talks. We'll have Anubhav here. I have Anubhav here with me, who's going to talk about the cluster balancer. We'll have him introduce himself. Logistically, if you have questions, just type it into the LinkedIn comment box. Don't feel shy. You can just say hi or say it was awesome or whatever it is. The presentation was awesome. All of that stuff. We'd love to hear comments from you. And you can also join our community Slack, yugabyte.com/Slack, and you can drop in the question there, and we'll be looking at that as well. So, Anubhav, do you want to quickly introduce yourself, and we'll get the show on the road?
Sure. Yeah. So thanks for the intro, I guess, Karthik. I'm an engineer on the DST team, which is Distributed Storage and Transactions. And yeah, as Karthik said, I'm based in San Francisco right now, and today we're going to be talking a little bit about cluster balancing. So I think if that's okay, let's jump right into it.
Yep. What do you have for us?
All right. Okay, so today we're going to start by talking about what the cluster balancer is, and then going over some common scenarios under which it becomes active. And then we're going to see a demo which shows those common scenarios along with some placement policy stuff. And finally, we're going to look at some flags that we can use for throttling the cluster balancer if we have some time near the end. Okay, so let's start right off with what is the cluster balancer. At a high level, the cluster balancer handles the distribution of data and queries to the nodes in a cluster. What that means is if you have 3 nodes, you usually want your data to be spread equally across those nodes. And you want the queries that are accessing that data to also be spread across the nodes. That way you're making full use of your resources. The cluster balancer doesn't actually do much in a static cluster. The interesting cases are mostly when the set of nodes in the cluster is changing. So you're adding nodes or removing nodes either voluntarily or involuntarily, like if a node goes down. So that's what we're going to be looking at today. Briefly, some of the examples are scale up, where you might want to distribute your data to your new nodes and also move your queries onto those new nodes. Scaling down, where you want to remove your queries and your data from nodes that you want to remove from your cluster. Upgrading a node, where you might want to temporarily stop queries from hitting a node, but maybe not move data off while you try to upgrade the node's OS, for example. And a prolonged node failure. This can be an unplanned failure where we want to quickly redistribute queries away from a failed node and eventually move all of the data off of the node. Before we get started, I want to do a little bit of a digression on terminology. So tables are going to be divided into tablets, and a tablet, which is also sometimes called a shard, is a group of rows in a table. So you can see on the right, the table table 1 is divided into tablets T1 through T3, and table 2 is also divided into 3 tablets. Tablets themselves are distributed across tablet servers, and a tablet server, T server, and node, these all mean the same thing, so I'm going to be using them interchangeably. And each tablet has 3 distributed replicas. These are distributed across tablet servers, and one of those replicas is a special leader replica, which will coordinate writes. So it's important to keep those balanced too. If a tablet has more than 3 replicas, we say that it's over-replicated. And if it has less than 3 replicas, then we say it's under-replicated. Both of these scenarios are not desirable because over-replication means you have more space, you're using more space and resources than you need, and under-replication means you're more prone to failures. Okay, so that being said, let's talk about why we actually want cluster balancing. So the cluster balancer works by moving tablets and tablet leaders to get an equal number of tablets and tablet leaders on all nodes. So the reason we want balanced tablets is because each tablet is going to require some sort of resources. These can be disk resources like disk space. It can be network. It can be disk I/O. It can be CPU. So we want those to all be balanced. And let's take a look at why. On the cluster on the left, we have a node 1, which has 4 tablets, and nodes 2 and 3, which each have 1 tablet. So this is not a balanced cluster. And on the cluster on the right, we have each node having 2 tablets, which is a balanced cluster. So let's imagine there's a sudden increase in load. On the left, node 1 is very likely to hit a CPU limit, while nodes 2 and 3 still have a lot of CPU to spare. So this means that any queries that go to node 1 or touch node 1 are going to be slow, or they might even be rejected because of CPU pressure. On the other hand, if we look at the cluster on the right, which was balanced, all of the nodes have scaled up equally, and the cluster is functioning as expected. So I've put CPU usage on the axis here, but really you can imagine this could be any sort of disk IO as well, or network cost, right? So that being said,
and just to clarify, Anubhav, so what you're saying is that the cluster balancer acts to transform something that's on the left to something that looks like on the right.
Correct. Yes.
Got it.
Yep. So yeah, balancing load is very important to cluster stability for that reason. And I think we can start looking into some of the cases where that I mentioned before. So let's start with a simple case of scaling up a cluster. Let's say you have a big event coming up and you decide to over-provision your cluster to prepare for an increase in load. In this case, in this example, let's say we're just adding one T server. Let's call it T server 4. This case is actually really simple. You simply have to add the node to the cluster, and the cluster balancer will automatically move some tablets from the existing nodes to the new node in order to maintain balance. So here it moved tablet T1 from T server 1 to T server 4, and then it's going to move tablet 2 as well. So you can see now the tablet counts are roughly balanced. The opposite direction, which is removing a node, that requires one additional step, because if you were to imagine just taking away T server 4 spontaneously, you would end up in this situation where tablets T1 and T2 are under-replicated, which means that they only have 2 out of 3 replicas, and so they're more prone to failure if one of T server 2 or T server 3 goes down. So if you were taking down multiple nodes, you might even generalize this to say that you might take down a majority of replicas, and in that case, your tablet data wouldn't just be under-replicated, it would be unavailable. So to avoid all of this, the cluster balancer, we will first blacklist the node to be deleted. So in this case, we'll blacklist T server 4, and what that does is it signals to the cluster balancer that it should try to move replicas off of the blacklisted node, and it should avoid putting any new replicas onto the blacklisted node. So in this case, it'll move T1 and T2 away. And once all of the replicas have moved off of the blacklisted node, then we can safely remove it from the cluster without any user-facing impact.
So one question, Anubhav. So you're talking about blacklisting or draining a node, right? Where you move both the transactions being processed by the node, but also the data that's present on the node. They both move over to other
Correct.
Nodes. Yeah. Is there a version of the operation that the cluster balancer can do where it only moves the transactions, but not the data?
Yeah, so we can kind of look at that here, where we have the node upgrade scenario with the leader blacklist.
Got it. Okay.
So
convenient. All right, let's do that.
Yeah. So node upgrades are kind of similar to downsizing a cluster in that you're still intentionally removing query load from a T server, but we expect the nodes to come back quickly. So maybe we don't want to take the expensive step of moving all of the data off of the T server itself. So a blacklist is maybe too heavy-handed of an approach. In this case, we have something called the leader blacklist, where if the tablet leaders are indicated by these red borders here, we're going to first add T server 3 to a leader blacklist, and the cluster balancer will read that and use that as a signal to move the leader of T3 over to a different T server. So T server 1 or 2 would have worked. In that case, if we want to do a node upgrade, we can now do the node upgrade on T server 3 and know that the operations are going to T server 1 and 2 and are not going to T server 3. So again, you're not going to have any user-facing impact here. So we do the upgrade, we can remove it from the leader blacklist, and then the cluster balancer trying to balance tablet leaders across non-leader blacklisted nodes will now move the leader back to T server 3.
Got it. So is it fair to say that the tablet leader balancing aspect of the cluster balancer is more for transactions and making that even query
Yes.
processing? And
there is definitely some load still for, if you have a write, it has to be replicated to all of the servers, but the connections will be going to the leader. So balancing the leaders is very important for balancing the load for queries and transactions.
Awesome. Thank you. All right, let's keep going.
Yeah. Okay. And the last case I wanted to mention was if you have a prolonged failure. So this is a case where a node goes down because of maybe, let's say, a power outage. And in this case, Raft, which is the protocol dealing with the tablets, will quickly notice the failure and will move any tablet leaders away to another node. This happens very quickly, almost in 3 seconds. And then after this happens, it's possible that the node comes back up because the node failure was something like a temporary network blip. In that case, we're fine and the leaders will move back. But if not, we don't want to stay in this state with only 2 out of 3 replicas practically for a long time. So the cluster balancer will automatically mark the 4th T server as dead after some amount of time. And by default, it's 1 minute. and it'll move those replicas over to another node so that we have 3 out of 3 replicas again. And we can look at all of these cases now in the demo. Before that, any other questions we have, Karthik?
No, let's. Oh, okay. So there is a question
Okay.
that Jim is asking, which is, can you explain the differences between the cluster balancer versus a load balancer?
Okay, sure. So I think a load balancer is more of like a network level device that you might have, whereas the cluster balancer is an internal Yugabyte specific component that deals with moving tablets, and not necessarily just routing connections, but moving underlying data as well.
Got it. So I guess in a more literal way, when a user issues a query, it'll hit, let's say it hits a load balancer. The load balancer is responsible for spraying that query across a set of machines, right? Like a set of nodes. Whereas the cluster balancer is responsible for how to move data and transactions that the various nodes operate over a period of time. So it's not like real time ready, but it's more like in the background, making sure everything is even. Is that fair to say?
I think so, yeah.
Okay, awesome. Hopefully that answers Jim's question.
Okay, right. So we have the view of a cluster I've started here. It's a 3-node cluster that I've started with YugabyteD. And you can see we have 3 nodes in 3 different regions or 3 different zones. We have 1 node in zone A, 1 node in zone B, and 1 node in zone C. 0 write-ups because I haven't started a workload yet that I'm about to start. And we can also see that the leaders and the total number of tablets are balanced. I've also added the time since the last heartbeat. This will become a little important when I show you the prolonged node failure, and showing that after a minute, we'll eventually move the data off of the tablet, off of a T server. Okay, so I'm going to start a workload now, and this is a very simple workload called SQL inserts that you can find on our YB sample apps. Essentially, all it does is it inserts a unique string values. It's just a simple key value insert. I'll give it a second, and then I'll refresh the UI, and we should be able to see the write operations go up. All right, so we can see that the write operations have started increasing on the cluster. We can also see that the table that was created was evenly spread across the cluster, across all 3 nodes. So let's go into our first scenario, which was adding a new node to the cluster.
I think it's probably worth noting that the total write operations per second on each of the nodes is the same, right? Like, and does this workload do any reads and above, or just doing writes right now?
This one is just doing writes right now.
Got it. Okay, so that's why we're focusing on writes. Got it. Let's keep going.
Okay, and I'm going to start adding a 4th node to the cluster. This node is going to be added in zone C. So I want you, before I add the node, to think about what might happen when I add a node to zone C. Which tablets might move over?
So yeah, why don't we just talk about that before you add it? So right now, the way this is placed is a multi-zone cluster, which means the data is all the data has 1 copy in zone A, which is on the first node, 1 copy in zone B, and 1 copy in zone C, right?
Yep.
And when you add a node to zone C, what it says is you have to keep that copy of the data in zone C, but you have 2 nodes, so you can spread the data in zone C from 1 node to 2 nodes, as opposed to, but the other 2 zones still just have 1 node. Is that fair?
Yep.
Okay,
and
got it.
So I've added the node now. Let's see.
Okay. Okay. Yeah.
Yep. So we can see the 4th node is added here. It's also in zone C. And as you can see, the write-ups have gone down slightly. It's been spread across all of the nodes. And you can see that each of the zone A and zone B nodes both have 25 tablets, and the other 25 are split between the 2 on the 2 T servers in zone C.
Got it. So maybe another minute here to summarize, right? So the data is split across 2 nodes in zone C, but the transactions per second are evenly spread across all the 4 nodes across the 4 zones.
Correct. Okay. So yeah, we can see that it's moved over. And just to reiterate what Karthik said before, if we were to move some of these replicas from zone A to zone C, that would be problematic because we would have 1 replica of the tablet in zone B and then 2 in zone C. And we don't consider both of these to be independent, both T servers in zone C to be independent failures. It's possible that they fail at the same time because of a massive power outage or an earthquake or something like that. And if that failed, you would only have 1 out of 3 replicas. So to avoid that case, we make sure that we only move from the node that was already in zone C to the new node that we're adding in zone C. So that's adding a tablet. Now let's look at the scale down operation where we remove, that's adding a T server. Let's look at removing a node or removing a T server. So we had the blacklist, which we added a node to. And what that does is it tells the cluster balancer to not use that node for hosting data. So I will add it now. And we should be able to see the tablets move back. So you can see now we have 9 tablets and 18 on this. If I refresh again, 6 and 20. And if I keep refreshing, we'll move all of the tablets from zone 4 back onto zone C, so from T server 4 onto T server 3. It's just like T server 4 didn't exist in the cluster right now. So if we wanted to remove it, now would be a safe time to remove it because it's not hosting any data.
Makes sense. Makes total sense, yeah.
And you can see also that the write-ups have correspondingly gone to 0. So we're not using that node at all. Okay, I'm going to remove it from the blacklist now. So we'll see the data move back onto it. And after that, I'm going to show you the case where we had a node upgrade, which is when we did a leader blacklist and the leaders move off of the node, but the data itself remains on the node. So let's see, is it balanced? Oh, sorry, I entered the wrong command.
So Frank has a question in the meanwhile.
Okay.
Which is that the slide said the new followers are created after 1 minute when the zone was down. Isn't it 15 minutes by default? Log min seconds to retain, or was it something different?
So yeah, so Frank, there's the follower considered unavailable after 15 minutes, and that's on a tablet level. And then we have the T server minimum seconds where we don't have a heartbeat from a T server. So there's both of those protections in place. If an entire T server is not heartbeating for a minute, then we'll move over the tablets, or we'll mark it as dead and move over the tablets. But if it's just one tablet, for example, there's just some error on that tablet, then that tablet will be re-replicated on its own, and it won't affect the rest of the tablets on the T server. By the way, I removed the node from the blacklist, and we can see that the writes are back to being spread evenly, as are the leaders, as are the tablets. So let's go to the blacklist now, the leader blacklist, sorry. And I'm going to add this node, the 4th node, to the leader blacklist to simulate, let's say we want to do a node upgrade. Very quickly, you can see that the leaders have moved off of this node onto the other nodes. So if I refresh one more time, you can see that the write-ups have gone to 0.
Yep.
Again, this node isn't taking data, isn't taking queries, but you can see that the total number of tablets is still not 0. That means it still has the data. And once our upgrade's complete, hopefully quickly, we can remove it from the leader blacklist, and then the leaders will move back onto it. And we won't have to have moved any data. It was just a logical operation.
Makes perfect. This is the time when it's okay to restart this.
Correct.
For an upgrade or something. Yeah, makes sense.
Okay. And we're back to a balanced state. And now I'm going to do the case that no one wants to see in their production cluster. I'm going to kill the 4th T server process, and we're going to see what happens then.
Waiting game.
Yep. So I've killed the process. Almost immediately, you can see that the time since heartbeat has gone up, right? This is the time since the T server has heartbeated, and very quickly, the leaders have moved over to the other nodes. The data is still on the other node, but the leaders have moved off. So that means you're still getting throughput, you're still getting queries that are able to access valid leaders, but the data is still there. There's still a possibility that this was just a 5-second network blip, and it'll be resolved shortly. But if you wait for longer, which is the 1 minute period, and that's all configurable, by the way, it doesn't have to be 1 minute. You can set it to 30 seconds if you want to move data off quicker and you have smaller tablets, or if you have large tablets and you really want to avoid moving data unless absolutely necessary, then you can set it to a longer time period. So we'll see as it hits the 60-second boundary that this node will get marked as, instead of the green check mark, which is healthy, it'll get marked as dead. As you can see, it's marked as dead here. And now the cluster balancer will start to move these replicas off of the fourth node, which it now believes to be dead, and onto the other nodes.
So in this case, you're setting the time window to be a minute, but the default is 15 minutes, right?
So I'm setting it to be a minute. Sorry, the default is already a minute for it being marked dead, but for 15 minutes is how long it takes before it's considered unavailable.
Got it. Is that still the case here, or like?
Actually, I think I made a change just before the presentation that we still need that that flag to be considered unavailable, which is why it's not moving the tablets right now. But if that flag were if we were to wait for 15 minutes, it would, but I'm not going to wait 15 minutes. I just wanted to show that this is what happens.
Okay, got it. No worries, no worries. So Misha asks a question. She missed the beginning of this presentation, and so the YugabyteDB dashboard we're looking at, what is it?
So the Yugabyte dashboard, it shows all of the nodes in the cluster. It also shows an overview of the operations in the cluster. It's kind of a high-level view of what's going on in your cluster, so you can quickly identify any sort of problems. And it also, sorry.
Yeah, and Misha, this tool is the new tool we are releasing. It's called YugabyteD. We've been adding more and more stuff to it. This is just the default open source product. So you can just download it right now and run it on your laptop, and you should be able to see this. But yeah, keep going on above. Yeah.
Yeah, that's pretty much all I had. You can see some high level views, like what kind of fault tolerance do we have? So in this case, availability zone fault tolerance, which means, well, no, if one availability zone fails, then our data is still fault tolerant. Total memory, total disk. Yeah, a lot of useful features. And if you've used our old UI, this is definitely a lot easier to use, easier to look at. From the nodes view, I can, for example, I can edit the columns, and I can see, maybe I want to see the memory used by each server, so I can see how much memory each server is using.
Awesome. So one other question that it's I think it's YugabyteD. So
yes, it's called YugabyteD.
YugabyteD. And Misha, you can just find it in our documentation as well. I think somebody can post a link, hopefully. Okay, actually, Jim just posted a link. Jim asks a question, which is, what tool were you using to blacklist? Is it YBadmin or?
Yes, I was using the YBadmin command line. If you have YB anywhere, then that'll automatically do that if you try to add new nodes. But I was manually doing it with YBadmin.
Yeah, and Jim, in terms of the roadmap, we are adding this as native support with the YugabyteD command lines rather than go to a separate tool. So these are things we're just incorporating into to simplify the user experience. All right.
Cool.
Fantastic.
Do we want to go back to the flags, or any other exploration around here you want to do, Karthik?
All right, let's see. So it'll take 15 minutes for these tablets to move up.
Yeah, it'll take some time.
So maybe we don't need to.
No, we don't need to wait for that. Yeah.
We already did restart this and show what really happened, et cetera, right? We already did that. Maybe one thing to look at is, can we go to the databases and look at like what is the let's go into the Postgres database, and let's go into that, and we can look at which exact tablets are under replicated, and if we start the node, right, like, can we see that these tablets auto re-replicate themselves?
Yes, we can. All right. There.
Okay, this is because I guess the tablets already had the data, and so it didn't really have to do any bootstrapping. It can quickly join and catch up on the leftover writes. Is that right?
Yep, that's correct.
Okay, fantastic. Awesome. So let's see if there are other questions. Yes, there is a couple of questions. Okay, Jim nicely says, awesome, I agree. Nagender asks a question. What is the main difference between YugabyteDB Anywhere and YugabyteD? So Nagender, think of YugabyteD as the open source. It's the just the way it's a daemon process. So like the way you have MySQL, the MySQL-D or Postgres, YugabyteD is the process you use to start the database in the more simplified user experience that we're thinking about. So instead of starting master and T server and all of that stuff, you just do it with one process. Whereas YugabyteDB anywhere is actually a DBAS tool. So it does like, it spins up machines, it understands disks, it understands, how to do nightly backups, it does key rotation for encryption. So it does a lot more of DBAS-like functionality. So hopefully that answers your question. And thank you, Jim, for posting a handy comparison screen, which compares the different products. Okay, so maybe we go back to your slide, I think, like on what are some of the other things that you can do to control the cluster balancer, right?
Sounds good. So we definitely have a lot of flags that we can use to control the cluster balancer. You don't have to look at these in too much detail. I just kind of want to go over the high level of what they are. They essentially control the trade-off between how quickly the cluster balancer balances the cluster and the overhead it takes in the system. So there's the frequency of how frequently the cluster balancer runs, which is by default once every second. And that's just how often it runs, not necessarily to make a move, but to take a look at the system and see whether there's anything that needs to be moved. And then per run, we have some throttles on how aggressively we can trigger new moves of tablets. So the max number of concurrent adds we can do per run or leader moves per run. And then finally, we have actual controls on how many can be ongoing at one time. You don't want to overload your cluster with just moving replicas around. So we have controls on the max number of tablets that can be bootstrapping, and those can also be limited by network usage instead of just number of tablets.
And disk bandwidth also, right? Like, it's
yeah.
The rate limit is both the bytes per second is network and disk, right?
Yeah.
You don't overwhelm either. And I think this is specifically important for shared disk, like the persistent disk scenarios, like an EBS volume or that type of disk, because your IO is also throttled in these cases. So, okay. So one question that Piet has, which is in your demo, the question is the data we see in the demo, is it coming from a SQL query or from some other interface into the T service? Like I'm guessing Piet is asking about, like, he's asking about the UI itself. So Piet, I think it is coming from mostly other APIs into the cluster. So these are more like protobuf APIs into the cluster to extract various information, sometimes REST APIs. So it's more administrative in nature. If you go back to like the demo view,
Yep.
like Anubhav, yeah. And if you go to let's see, activities is not yet in performance. Go to the performance on the left. Yeah. And if you click on live queries.
I've stopped the workload right now, so we won't see anything, but I can start it again.
Or go to slow queries. Actually, no, go to slow queries. That's fine. Go to slow queries. Yeah, we should be able to see something here. Yeah, and you can click on any one query here. And yeah, there you can take a look at exactly what is running. Obviously, this is a visualization on top of PG stat statement. So this actually uses SQL queries, but the data is pieced together from various parts of the cluster. So some using protobuf and REST APIs and some using SQL queries. So hopefully that answers Piet's question. Omkar had a question, which is only data migration needs to happen when node 4 dies. And I think I think Omkar says when node 4 dies, and is the new data written on the tablet, master tablet on node 4. I think it is true that data migration happens only when a node is added or fails. That's fair, right, Anubhav?
Yep.
Okay, but the data is written into the T server, like as a process, not the master. But anyway, that's just an internal detail. Hopefully that answers. There's a lot of discussion going on as well. Okay, so yep, I think all of the questions answered. Let's keep going.
Yep. There was just one last slide I wanted to show, which is other things that you might want to be aware of about the cluster balancer, but we necessarily don't have time to go through all entirely today. So a lot of the cluster balancer's job is to deal with placement, like availability zones and regions. I might have, for example, a cluster-wide placement policy saying that I want all of my data to be, even geo-distributed. I might want one replica in the US, one in the EU, one in APAC. But for data sovereignty reasons, I might want just one table has to be in the EU only, or one table has to be in Canada or something like that. So a lot of the cluster balancer's job is to deal with placement information like that. And we can also leverage that information to choose when we add a new node, which node to copy data from. So for example, let's say I'm starting to scale up a cluster and I had the zone C node. Well, it's preferential for me to copy the data from the replica that's already in zone C if it exists.
Yep, absolutely. Given that all the nodes are consistent and it's transactional, you can just do that. Yeah, makes sense.
There's also priority zones for tablet leaders. If you have an application that's in, for example, US South, you might want all of your tablet leaders there so that all the writes can quickly get to a leader. And we have multi-level priority as well. So you might say that, well, if South isn't available, I'd like East, and if East isn't available, then West. So there's that complexity, but usefulness as well. There's also balancing across multiple drives on one node. And then I put some future work here, which we have some thoughts about, which are, you might want IO or disk-based cluster balancing because maybe not all tablets are created equal. You have a hot shard problem, which you shouldn't, but if you do, well, we don't want to be susceptible to failure because of that. So we might want to consider balancing tablets based on IO and disk usage as well. And then there's a bit of work on automatically scaling those flags, which we saw for throttling remote bootstraps, so that instead of saying, I want 10 remote bootstraps going at the same time, I want one per node or one between every pair of nodes. That way you're maximizing the use of a large cluster while not penalizing smaller clusters.
Awesome. Fantastic. I think this was really nice. A lot of interesting discussion going on LinkedIn, but I think that brings us to time. I don't know if you had anything else. Yeah, I think
that's all I had. Thank you.
Right, great. Yeah, thanks a lot. And it was a fantastic presentation, obviously, lively session, a lot of interesting info. And thank you for showing that in, a clean set of scenarios. It was wonderful. Once again, folks, thank you for all of those who joined. Thank you for the questions, comments. It was really good. Again, join us again next week, same place, same time. We have another YFTT talk scheduled then. In the meanwhile, if you have questions, continue to post it on LinkedIn, or you can join our community Slack. It's as it shows on the screen, yugabyte.com/Slack. And we'd love to hear from you. All right. Thank you, everybody. Thanks a lot.